Start the recording. So how we all doing on the last day of meeting anyway of the class? The last day, hopefully you'll be thinking about this. Will be over the weekend when you're working on the homework. You all doing okay? You all can hear me okay? Okay, cool. So I wanted to start by seeing if you guys had any questions about the lab, the take-home final, the homework, anything at all, because this is the last time I can kind of talk to you guys as a group about any of that stuff before the end. Just as a reminder, what's left? Do Monday, Lab 5, which is extra credit, homework 5, and the final. What just happened? Not optional. So if you guys have any questions about the labs or the homework or the algorithm stuff we've been doing, I'm gonna do some more algorithm stuff today, talking about speed and things like that. But if any questions about what we've done in the past or stuff that you've run across as you've been hopefully working on the test and the lab and stuff, this would be the time to ask those kinds of questions. One other thing I wanted to bring up was because this happened to somebody today who said, "Oh, I don't know if any of the homeworks that I sent you have gotten to you," and they hadn't. So everything you guys have sent to me, I have responded to with a grade if it's a homework or comments if it's a lab. And the labs are just kind of grading for completions if you did it. You're not losing points for me correcting it. I'm just making sure that you understand where we're at with the labs. But all the homework's been graded except for this last Scratch homework that was due this week. I'm going to try to grade that tomorrow. And obviously the new stuff. So the point is, if you have not gotten back responses from me or grades from me or anything like that, then I did not get them, and you need to make sure that I get them before the end of the semester. So if you've had problems with that, the time to fix that is now, not after you get a bad grade on the final grade. Okay. If you want me to tell you what your grades are on the various labs and homeworks and things, send me an email and I'll give you the rundown. And if that disagrees from what you're thinking you have, let me know and we can figure something out. But make sure you check, I guess, or check your emails or something, because I don't want to have a situation where you guys think you sent me a whole bunch of stuff all semester and I never got it. So I think you haven't done anything all semester, and then you don't get credit for the stuff you've done. Okay. So, all right. So today, the end. Yay. Yay or boo or whatever. What I want to do is finish up the algorithm stuff. Focusing on ways to measure speed. So one of the points I was trying to make last time with that long thing about binary search was that the binary search was faster in some sense. We talked about in the worst case it's faster, right? In the worst case, a binary search does less steps than a regular sequential search. I want to kind of get a little more, a little less fuzzy with the description of better and faster and less steps today. I'll do some examples of other algorithms. I'll do if time examples from the lab. Again, if there's anything you want me to go over, let me know. Okay. So here's where we're at. Okay. Last time we did a lot. I did a lot of talking about searching. Searching was looking in a list of items to find the position, or I'll just say to find a specific thing or determine that it's not there. Okay. That's meant to be a parentheses. And the two algorithms I gave you was, I don't know if I used this name or not, sequential search. This is the one that looked at everything. And where we ended up was it was slow and always works even if I know nothing about the organization of the list. Okay. This is the one where I dropped all the cards on the floor. And I said, if I drop all the cards on the floor, I have no idea where anything is. The only way to be sure that I find it is to look at every single thing. That's what I mean by always works, even if I know nothing about the organization of the list. All right? And then the other one was binary search. This was the one where we repeatedly chop the list in half. Okay, and this was faster but only works if the items are arranged in order. Right? The whole point of being able to look in the middle and decide if that middle was too high or too low, and therefore I can throw away half the list, was based on me knowing that everything, for example, to the left of the middle was smaller, and therefore if the middle was too small, everything smaller than the middle was also too small, and I can throw it out. If you don't give me a list that's in sorted order, I can't do that, and the stuff I throw out might happen to have the thing I want, and I'll be screwed. Okay, so when I say faster, remember I mean the number of steps the algorithm takes in the worst case. And by worst case, we mean the situation where we get maximally unlucky. Okay, this is how many steps could it take? Okay. How long could I be waiting to go through every single card? Okay. And the other thing we're going to say that I didn't really talk about last time, but I kind of mentioned it in the examples. I'll say it this way. How do the steps change as the input size gets bigger? Okay. How many more steps do I have to do if you give me a bigger list? That sort of thing. Okay. So, for example, sequential search. In the worst case, if I have 100 items, I need to look at how many things of them. If I hand you a list of 100 items, if I'm maximally unlucky with sequential search, how many items do I have to look at in that list before I'm sure it's there or not there? 100, right. The entire, whoa, I just lost my screen here. The entire list, okay? If I have 200 items, how many do I need to look at? If I hand you a list of 200 things, how many, in the worst possible case, do I have to look at before I'm sure I found it or not? Right. You see where this is going, right? If I hand you 1,000 things, so we write the 200. If I hand you 1,000 things, how many things do I have to look at before I am sure I found it or not? Yeah. So what we do is we say, in general, let's make this number be an abstract variable. We'll call it n. If I have n items, where n is any number in the world, how many things do I need to look at? When n was 100, you said 100. When n was 200, you said 200. When n was 1,000, you said 1,000. So I need to look at all n of them. Does that make sense? So now binary search is harder because of how we don't have a good intuition, but it'll be less than n though, right? If I hand you n things, I ought to be looking at less than n items, yeah? If I hand you 32, I'm picking 32 for a very specific reason. If I hand you 32 items, in the worst case, I throw out half of them in the first step. I don't find it, I get unlucky. I have to. It doesn't matter whether it's the high half or the low half. I go to a list of 16, right? I throw out half of my 32 the first. Actually, I throw out more than half, but it's easy to do the math if you just throw out exactly half, okay? Because in the middle, I'm throwing out really half plus 1, but this is easy to understand. I go to a list of 16. If I don't find it in my half-size list of size 16, I look for it in a list of size 8. If I don't find it in my half-size list of size 8, I look at it in a list of size 4, and then 2, then 1. And if I don't find it all, remember I had a list of size 0, okay? So 1, 2, 3, 4, 5, 6, 7 things. 7 things to look at. Or 7 things to check. You don't really look at this at this case. But if you buy that I kind of have 7 steps or passes through the binary search, right? If I hand you 64 items, how many things do I look at in the worst case? Okay. If 32 items got me 7 passes through this algorithm, 64 items, what's the first thing I'm going to do with a list of 64 items? Assuming I get unlucky. Right. And since finding in 32 means I have 1, 2, 3, 4, 5, 6, 7 things to look at, that means 64 items was 8. Right? Do you see how I'm going through this list? Because this is how I'm mapping out the sizes of the list after I do every chop. Does that make sense? This is a good time to ask questions about how binary search works if you're not sure. Okay. So it's hard to see this. If I have n items to start with, okay, my list sizes are n, the whole list, then I chop it in half, and I get n over 2, half the list. Then I chop that half in half and get n over 4. Then I chop that quarter in half and get n over 8, dot, 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 1, and then 0. Okay? Now, I don't know if you remember this, but we had a formula for how many times we take a number and chop it in half until we get down to 1. Okay? Log to the base 2 of n is the number of times we can chop n in half until we get to 1. Okay? This is a little more than that because I've got to do one more to get to 0 and things like that. And I do one on the full list before I chop. So, so the point is, binary search takes about log to the base 2 of n steps to search a list of size n. Okay? So in CS, the way we say about is with what's called big O notation, because it has a big O. And so big O of log to the base 2 of n is about log base 2 of n. Okay, so the big O means about that many steps. So I'm not going to worry whether I'm off by 1 or 2 or something like that. But this involves chopping in half repeatedly. Okay. So the whole point of the big O notation is to not worry about whether, so sequential search is order big O of n steps, about n steps. I don't care whether it's n plus 1 because I have one more step to say no, I didn't find it. I don't care if it's n minus 1 because it's about n. Okay, the graph of input size versus steps for sequential search is a line. whether it's an n-1 line or an n+1 line or even a 2n line, I don't care, it's a line. The graph for binary search flattens out really fast like this, because if this is 32 and this is 64, this went up by 1. And if this is 64 and this is 128, way over here, this goes up by 1. Okay? So order big O of log n algorithms always have a lot less steps than big O of n algorithms, because doubling the size of the list adds one more step here. Double the input, add one step. Where order n, like the sequential search meant, was double the input, double the work. Okay? So the homework and the lab talks, and probably the test, talks about writing the number of steps in big O notation. All that means is, can you write down the number of steps in some way that's relative to the input size, like this or like this? Okay. So so far so good. Before I keep going, you get what the big O thing means? It's just a way of measuring the number of steps you do as the input gets bigger. Okay? Questions so far? Okay. The big O levels to care about. I think these are the only ones I inflict on you on the lab or the homework or the test, I think. There is something called O of 1, order 1, big O of 1. That means one step about on all input sizes. No matter how big a list you hand me, it takes about one step. So an example of this would be find the first thing in a list. I don't care whether the list has one thing or 10 things or 10,000 things. The first thing in that list I can find in one step. Boom, there it is. Right? Order log to the base 2 of n, which I'm going to probably write order log n and forget the base 2. If I do, that's the same thing. I mean the same thing there. This is binary search, double the input size plus one step. Then there's order n, things like sequential search, double the input size, double the work. There are things that are O of n squared. If you do an order n thing n times, you get order n squared. I'm going to come back and talk to you, give an example of this one in a second. And there's theoretically order n to the third and things like that. N squared, double input size, do 4 times the work, because 2 squared is 4. This theoretically order n to the third, order n to the fourth, dot, dot, dot. I don't think I make you do much beyond squared, but these all exist. And then the biggest one that we're going to talk about is order 2 to the n. That's the function we use to get combinations out of bits, remember, for the awesome formula of doom. So add 1 to n, double the number of steps. Okay. So in the lab, or I think it's the lab, might be the homework, I have a question. Now I'm curious where I put it. On the lab or on the homework. I'm looking it up right now. That's a homework question. Okay. Homework question 2B. Just so you're ready for it. Okay. Design an algorithm that displays all combinations of an n-bit number. So I hand you n, you hand me every single bit combination, or the algorithm hands me every single bit combination there is of that number. Okay, so we know from the awesome formula of doom way back in the first day or two of class that 2 to the number of bits you have is the number of combinations of bit patterns with those bits. With those bits. Okay. So this algorithm, which we haven't written yet, should take big O of 2 to the n, that's an n, steps. One step to spit out each bit pattern. Does that make sense? So this is an example of an algorithm that's order 2 to the n. See how I got that? I haven't showed the algorithm yet. I will. But you kind of see how it has to have that many steps because it's got to spit out that many things. You buy that? Here's the algorithm, just so you can kind of see an example of a 2 to the n thing in action. I might give you another one here in a minute. Set algorithm. Write all 1-bit numbers. Easy. Okay. Until you have the right length of your bit pattern, write all your old bit patterns twice. Once starting with a 0, once starting with 1. And so what I do is I build it up bit by bit in the same way that I build up binary numbers, right? The way I get a 4-bit binary number is I take all the 3-bit binary numbers and see what the possible 4th bit could be by sticking a 1 in front of it or sticking a 0 in front of it, okay? So when I start with 1 and 0, for 2 bits, I get 1, 0 with a 0 in front of it, and I also get 1, 0 with a 1 in front of it, and that gets me all 4 combinations that I get with 4 bits. With 3 bits, I take all 4 combinations and I do them twice, and I write them all with a 0 in front of them, and I write them all with a 1 in front of them. And that gets me all combinations of 3 bits. And I can get all combinations of 4 bits by taking these 8 things and sticking a 0 in front of them, and then taking these 8 things and sticking a 1 in front of them, and so on and so on and so on. Does that make you buy that? See how the algorithm works and how you can apply the algorithm over and over and over again by repeating steps and doing the same kind of thing, and how the algorithm specifies what you have to do on the old steps to get the new steps? Does that make sense? Did I not? Oh, because this 0, 1 should be, yeah, so hang on. So I should have a here too. I copied the old things wrong, right? So that 0, 1 should have a 0 in front of it, and that 0, 1 should have a 1 in front of it. Yeah, yeah. My bad. Copy it correctly is also important. All right, so that's an example of an algorithm that takes order to big O of 2 to the n steps. Okay, I keep saying order because that's the CS term for it. I'll give you another one here in a minute if we have time. I do want to do an algorithm that takes order n squared steps. It's going to be sorting a list. Taking a list of stuff in some arbitrary order and arranging it so that it will be in order when we're done. Okay, this is going to take about n squared steps. I'm going to do an order n thing n times. Okay, first, before I get there, a substep. Finding the smallest thing in a list. I'm going to use this as part of my sorting. Okay, but did we do this yet? I don't think we did. Can you guys try to come up with an algorithm that finds the smallest thing in a list? So it's slightly different from sequential search, because for sequential search, I gave you a specific thing I want. Here I say, I don't know what it is, but I want to know the thing that's the smallest in the whole list. I don't know where it is. It could be anywhere, but I want to know what it is. Okay? So in general, what kind of algorithm would you have to follow to make that happen? To get to the smallest thing in the whole list? Yeah, you don't know anything about the order of the list. Let's say it that way. Yeah. So that's the right idea, right? The algorithm is going to look something like this. I'm going to be a little more exact about it. Point to the first thing. It's the smallest so far. As far as I know, the first thing on the list is the smallest thing. What I'm going to do is look at everything else and see if it's smaller. So now I'm going to look at each item in the list one at a time. If it is smaller than your smallest so far, update your smallest so far. So basically, look at every single thing on the list and remember the smallest thing you've ever seen. By the end, the smallest thing you've ever seen, if you see every single thing, has to be the smallest thing in the whole list, right? So when you've looked at the entire list, your smallest so far is the smallest thing overall. Right? So what do you think the big O of this is in terms of n? Your options are basically big O of 1, big O of log n, big O of n, big O of n squared, or big O of 2 to the n. Let me go back to the list of the big O's. So these are your possible big O's. I guess 2 to the n is a thing too, but it's not for this one. Which one of these does it feel closest to? How about that? N. Why? Right. And so this is order n, big O of n, because just like sequential search. Basically, anytime you look at everything I'll say at all n things, once, it's big O of n. Okay? It's about n steps to look at n things once, right? It's about n steps to look at n things twice too. Don't freak out by that. It's about n. Okay, you buy that? So before I go on, I want to make sure you guys understand that the n, because I would consider this to be the easiest big O level, the order n level, because looking at n things is big O of n steps. All right, questions on that? All right. So now back to sorting. Take the unsorted list. Find the smallest. This is step 1. This is step 2. Keep in mind that finding the smallest is itself an algorithm that itself has a lot of steps, right? Doing that thing we just did. Number 3, pull it out and put it on the back of our sorted list. Okay, go through everything to find the smallest, take it, pull it out, throw it in the back of our sorted list. Step 4 is if the unsorted list still has items, go back to step 2. And then find the smallest thing out of what's left and pull that thing out and stick it on the back of our sorted list. And then if we still have stuff, pull out the third smallest thing, and so on and so on and so on and so on. I want to give you an example of how this works. Suppose I hand you 5, 2, 1, 4, 6, and that's my list. Okay. Finding the smallest, I have to go through everything. That was the algorithm we just had. You're the smallest so far. Oh, wait, you're the 2 smaller, so it's the smallest so far. Oh, wait, 1 smaller, so it's the smallest so far. 4 is not less than 1. 6 is not less than 1. So when I get to the whole list, I found the smallest thing, and it's 1. Okay? Whoa. It's 1. So now I've got a sorted list that has just a 1 in it. And I've got my unsorted list that has everything except the 1, because I pulled out the 1. Start all over again. Go back to step 2. Find the smallest. So I walk through the whole list. 5 is the smallest so far. Oh, wait, 2 is smaller than 5, so it's the smallest so far. 4 is bigger than 2, so 2 is still the smallest so far. 6 is bigger than 2, so 6 is so 2 is still the smallest so far, so it's 2. I chop the 2 out of the list. I end up with a sorted list that was just 1, but I just put the 2 on the back of it. And an unsorted list, 5, 4, 6. See how this is working? Third time through, find the smallest. Five is the smallest so far. Oh, wait, 4 is smaller than 5, so it's the smallest so far. 6 is bigger than 5. 6 is bigger than 4, so 4 is still the smallest so far. I take the 4 out. I make my sorted list. B1, 2, 4. I make my unsorted list. B5 and 6. Next time through, I find the smallest. It's 5. I take the 5 out of here. So my sorted list is 1, 2, 4, 5. My unsorted list is just 6. Finding the smallest in the unsorted list means I end up finding the biggest because it's the last thing left. And so the sorted list is 1, 2, 4, 5, 6. The unsorted list is empty. And I'm done. Now, if there's anything left in the unsorted list, go back to step 2. Now there's nothing left in the unsorted list. I don't go back to step 2 and I stop. So, do you buy how this works? Do you buy this would work? It would take a lot more steps. But if I handed you a list of 800 things, we could theoretically sort them by following this algorithm, even though we'd hate it because it'd be a lot of steps. You see how it works, and it kind of makes sense. Okay. So now let's think about time. Okay. Think about. Boy, that's ugly. Think about number of steps. Okay. Finding the smallest. We said was about n steps. I have to look at everything. How many times do I have to find the smallest? If I have I had a list of 5 things up there, how many times did I have to do that find the smallest step? Five. So if it was n things, I have to find the smallest n times, right? So what I did was an order n algorithm n times, and so that makes this be order n squared. That's what n squared steps means. That if I do a thing that takes big O of n time, and I do that thing repeatedly n times over and over and over again, like on everything in a list, then that's n squared. Okay, and n squared, remember, is double the list 4 times the work. So if I go, so however many steps that sorting 5 things took, sorting 10 things takes 4 times as many steps. Okay, and you can imagine that because not only do I have more times to find the smallest, every time I find the smallest, I'm finding it through a list of more stuff, right? So you're getting hit in both directions. You're getting hit here and you're getting hit here. If you make the list bigger, you're getting hit both in the number of times it takes to do the finding the smallest and the number of times you've got to ask to find the smallest thing to do its work. Okay, so that's an example of another algorithm that has order n steps, order n squared steps. Okay, cool. Questions on that? Okay. All right, let's do some more examples. Another slow algorithm. This is something you might have seen before. It's called the Towers of Hanoi. It's a classic puzzle. It shows up in a lot of weird places like video games and things like that. The general idea is you're handed 3 pegs, and I can't draw these well, but on the first peg is some number of discs. These are discs on a peg, like with a hole in the middle of the disc. Okay. We can label these 3 pegs A, B, and C, these towers. The problem: get all discs from A to B, but rule 1 disc at a time. So I can't just take the whole stack and pick it up and slop them all down. I can only move 1 disc at a time. And rule 2, never put a larger disc on top of a smaller one. Okay? Have you guys seen this? Does this look familiar at all? I'm going to try to find a example of this online. That was an annoying game. Let's see what that spits out. Okay, good. I'm going to share my screen and show you this web page here. I found it by searching for Towers of Hanoi game. Okay. So you guys can see this? Okay. All right. So let me ask you a really, really simple question. Can I get any smaller than 3? No. All right, then I can't show this to you. How many steps do you think it would take? Let's pretend these 2 bottom discs aren't here, and all I had was 1 disc to move. How many steps do you think it would take to move 1 disc from A to B, following the rules? 1. Ta-da, right? Not hard. A harder question, I wish I could make this smaller, is how many moves it would take to move 2 discs over. So the top one and the bottom one. Okay? It's going to be more than 1, right? And it can't be 2 because why 3? Three's right. Just tell me what you did. Right. And so the first move has to move the smallest guy all the way out of the way. And then, right. And the second one, now I can move the second one over, and then I can move the third one back. Okay? That make sense? So the next question, this is hard. This might be hard to do in your head. How many moves does it take to move 3 discs? The fact that they gave you the answer here should be a hint, I guess. So they're saying it's 7. Does anybody see how you can do it in 7, kind of in general? You don't need to explain all 7 steps, but this idea that Jillian just had about moving the smallest one out of the way is a good idea. For example, what I could do is do the 3 steps it takes. Now that what we did was the 3 steps it takes to move the 2 to the place it's supposed to go, right? But suppose I did this. I did 3 steps it takes me to move 2 stacks off to the side, out of the way. Okay, still 3 moves, right? But instead of going to the middle peg, they're going to the out of the way peg. Okay, then I move the big one over. Then I've got to move these 2 guys back, and we know that moving a stack of 2 things is 1, 2, 3 moves. You buy that? You see how I did that? Okay. I'm not gonna click this to 4 yet, but how many moves do you think it'd take to do 4 discs? By the same process. Maybe a better question to ask is, what's the first big step of the 4 disc process? Maybe I'll write this for you. With 1 disc, do it, 1 move. Moving 2 discs, we said the first thing I did was move the top out of the way to C, the 3rd peg, move the bottom over, then move the top back to B, right? One step each, 3 steps total. Move 3 discs, we said move top 2 to C. That was 3 steps. Move the bottom. That was 1 step. And then move the top 2 that we pushed off onto C back to B, and that was 3 steps, and that got me 7. Right? So do you get how the way I'm explaining this, the way I'm building it? So far, so good? So how would I write 4 discs using the same pattern? What's the first thing? Well, except now it's not top 2. 3 discs was top 2. 4 discs, I have to move the top 3 to C. Right? Everybody but the bottom's got to get out of the way. All right? Then move the bottom. That's 1 step. And then move top 3 back to B. 7 steps. See how I did that? Move 3 guys out of the way, move the bottom, move 3 guys back. And so if we go back to the example here, and I go to 4, first of all, they tell me it's 15. Second of all, I've got to, it's a lot of steps, but I got to do a 7-step process to get 3 disks all the way over here, right? Then I do a 1-step process to move this guy here. Then I do another 7-step process to get those top 3 back to where they belong, okay? And then for 5, I'm not going to do 8. For 5, I'm going to watch them solve it. And so what they're going to do is this is all part of moving 4 disks. Well, they're going to go to the 3rd peg, I guess. You move 4 out of the way, you move the big one over, you move 4 of them back, okay? And inside, you have lots and lots of subproblems. It's hard to keep track of it all because remember, so that's 15. To move 5 disks, I move top 4 to C, and we said moving 4 was 15. Move the bottom. Move top 4 back to B, which we said was 15. Okay? And that's 31. Okay? So remember, though, moving 4 disks involves moving 3 disks twice and moving the bottom. Moving 3 disks involves moving 2 disks twice and moving the bottom. So it's a lot of stuff going on all at once. And I don't need you to, I'm not going to ask you to walk through a 5 or 6 disk tower of Sonoy solution. But what I want you to see is to move n disks, move the top n minus 1 to C, move the bottom, move the top n minus 1 to B. Everybody but the bottom goes to the spare peg, then the bottom moves, then everybody but the bottom moves back. Okay? This is an example of adding 1 disk doubles the work, which means it's a big O of 2 to the n algorithm. Okay, and so the reason I'm showing this to you, first of all, is that big O 2 to the n algorithms come up in a lot of weird places, and it's a different way of thinking. And I think things like the searching was pretty straightforward, and even the sorting was pretty straightforward. And this doing something by breaking it into 2 copies of something smaller is something that's different and worth seeing an example of. If I want to move 10 disks, that's about 1,000 steps, because 2 to the 10 is about 1,000. If I want to move 20 disks, that's about 1,000,000 steps. If I want to move 30 disks, it's about 1,000,000,000 steps. And so the point is, and this is kind of the end of the semester thing I want to tell you about, just because computers are fast and dumb, okay? Somebody asked me what the big takeaway for the semester is, and I think it's that computers are fast, dumb, algorithm executing machines. And so it's important to have your algorithm straight, because the computer is just going to do whatever your algorithm says, whether your algorithm is good or not, okay? But even if a computer is fast and dumb, there are some things that have very, very small inputs that lead to very, very large numbers of steps. And yes, the Towers of Hanoi is a simple, lame example of a toy problem, but there are real problems out there that really can't be solved by computers right now at large ends, because the best algorithms we know of is order 2 to the n, and it's not a matter of waiting for a faster computer, right? Doubling and doubling and doubling and doubling and doubling gets really, really big, really, really fast. Okay, 100 disks, just so you can get an idea. I don't even know what 2 to the 100th is. I'm gonna stick it in my calculator now. 2 to the 100th, according to my scientific calculator, is a 3, 6, 9, 12, 15, 18, 21, 24, 20, a 31-digit number. And so maybe if I make my computer 10 times as fast, I can get that down to a 30-digit number of steps, of seconds. But that's still a really ridiculous number of steps, right? So some algorithms out there are super slow, even on super fast computers, and it's because the algorithm's big O is slow, and it's going to stay slow no matter what the computer does. All right? Any questions on Big O or Towers of Hanoi or sorting or algorithms or anything? If not, don't forget to check and see if I've graded all the homeworks you've sent. Don't forget to do all of the homeworks and labs and tests that are out there. Don't forget that Monday is the hard deadline because I have to hand in the final grades by Tuesday at 4:30. The registrar doesn't give you any extra time. So ask questions. The earlier you ask questions, the more time you have to use my answers. Let me know if you get stuck. Good luck. Thanks for putting up with me all semester, and have a good rest of your summer.